Okay, let's resume. So this time, now that I have way more RAM, I've upgraded to 64 gigs of RAM and fully loaded up my 5090 with GPT OSS 120B just to see how this performs in comparison to the Quen 30B model. Now what's going to happen now what needs to happen is that we need to update our client configuration to state that we want to use GPT OSS 120B. We're still using the same 20 whatever we're not 20 64K context. I'm going to test this out by saying hi just to make sure that we can make that API request. Again, there's going to be a lot of tokens that will be processed. You'll see that it's beginning to process the prompt right now. It's going to take a bit because there are lots of tokens that client sends over, but we'll get there. Anyway, just to review what we were working on, we were just getting started on a design document to detail specifics about the NES, or not NES, the Game Boy, the Game Boy CPU. The reason why I say NES is because I did write an NES emulator in the past. So this is pseudocode for like a Python CPU simulated. What I think is next is we need to discuss how to implement every single opcode, basically things that go under here. So for every single opcode, we will handle it within some function in an if block, if else block that modifies some global state. Okay, global state. So we'll have some global state. That's basically the memory, actually emulated memory. So we can think of that as like a global variable. Global variable, an array. Okay, and in this case here it'll be array of 8 kilobytes. So but I guess not just 8 kilobytes, but it has a 64K address space, so 64 KB. Okay, each address represents 1 byte, therefore representing the address space of the Game Boy. Okay, each opcode. Okay, so each opcode will reference the global state to update the memory, and I guess not just the memory but registers. So we'll have the A. What else do we have? We'll have the AF, BC, DE, HL, and SP and PC registers. So we can go back here and say AF, BC, DE, etc. registers. So each opcode will reference the global state to update registers in memory and other pertinent or other important things that are shared. Okay. So then, yeah, that's the gist really. So let's see if we can get GPT OSS to do something with this. So look into design.md to understand the project. After that, improve this selected text to be more relevant to overall documentation purposes. Okay. So let's see how it does here to rewrite. Yeah, I think the next thing we can do immediately is to just start writing the CPU code and then refactor it later to be more, I guess, modular with the overall system. I think we could vibe code a little bit because we have this opcodes JSON and it has this design document here that it can use to just start writing some vibe code. Maybe we can have like a global state. So let's have like a source, and then let's have a folder called I guess CPU, and let's also have an init.py, and then let's also have maybe a folder in source for now called memory, and then we'll have an init.py there. Okay, then CPU, we'll have CPU.py, or actually let's call it that, CPU.py, or in fact let's call it GB CPU.py. Okay, so we'll have GB CPU.py here, and this is where we're going to be implementing the CPU, and in memory we'll figure that out later. But for now, wait, it says the file ends abruptly. Why is that? Wow, this is actually pretty slow. Oh, it's because I didn't save anything. Cancel. Okay. You know what? Let's do this. Let's do it again. Design.md. Here is the project details so far to get you up to speed. How can I improve or rewrite the section? How we implement each opcode to be more relevant for future readers that want to understand the project. Right now, I just want to give a summary in how we will approach individual opcode implementation. Okay, we'll just let that go again. As it's doing that, I'm just thinking, okay, well, we'll have a registers object, and then we'll also have the main CPU. So we can have a class register, right? A registers class, and then this could be something like AF, right? And that could be, in this case, it's gonna be an integer, and we can just set that as 0, and then we'll just follow with everything else in here, which is going to be BC, DE, HL, SP, and PC, and they're all going to be integers in this case. So BC is an int, that's also 0, and then DE is going to be an int, that will be initialized as 0. And I think usually they're just initialized with like random garbage values, but we'll see what happens. HL int 0, SP int equal 0, and then PC is also going to be a 0. So that's our registers class. Yay! It's gonna be very simple. Okay, and we can just hit them directly. So for example, we'll have registers object, that could be registers instance, and we could just have registers.af equals like 5, for example. Okay, so that's how we'll use it. Okay, so it has a rewrite. Let's see. So opcode dispatch. If else, a chain examines the fetch opcode and calls the corresponding handler. Global state, all CPU registers, flags, and the 64 kilobyte memory array are stored in module level globals that each handler mutates directly. Handler responsibilities. Each branch updates registers, memory, or other shared structures as required by instruction semantics. Okay, so recommended structure for future readers. Decoding dispatch, so two-step decode already described. Okay, dispatch table, replace a long if-else-if chain with a dictionary that maps an opcode integer to a handler function. Oh, okay, I think that's better. Like something like this. Okay, I'll take that. That's a good idea. Yeah. The main loop becomes, okay, so it becomes something like this. I think that's a great idea. Yeah. Okay. Cool. CPU encapsulation, CPU class keeps registers, flags, and program counter as instance attributes. Yep. Self.af, self.bc. Okay. So handler design, one function per opcode. Each handler implements the exact semantics of its instructions. Arithmetic, flag updates, PC increment. Common tasks such as setting flags, reading, writing 16-bit values, or performing signed arithmetic should live in helper mode. I think this becomes very opinionated, but let's just focus on documentation for now. Let's just focus on documentation of the immediate approach to opcode implementation right now. I think your idea about a dictionary of handler functions is awesome. Let's document that approach. Okay, let's do that. Act. Send. Okay, so let's work on that. Let's have it edit that, and then let's inform it on this is how we're going to do registers. We'll just have a registers class, and then we'll also have a CPU class. So class CPU. We're going to have a variable called registers that's basically going to be registers. So it'll be def init, okay, self. So we'll have self.registers. It's going to be a registers class. Okay. So then we can send back maybe like a get registers. Probably like get registers with like a code, for example. So get register self code. So code could be something like if code equals AF, for example. We can just return self.registers.af. Oops. And why would we want to do it like this? Because then it'll give us a chance to at least do some work before we actually return the registers. For example, let's say we want to do some masking of the integers to only like set the last 8 bits and so on, or like we want to get register A, so we only want to get the, I think, the high level bits, right? In this case, if yeah, the high level bits, or get register B, right? Get the low level bits. So we can document that. So lf code equals A. Okay, then we can say, okay, get the high level bits of AF, and then we can just pass here. We're gonna have the LLM finish that off. So something like B will be get the high level bits of BC, and then code equals C, get the low level bits of BC, and then say pass, then we'll just say pass, and then implement the rest here. Okay, so that's like a good start for it to start code generating things. For now, it's already starting to edit, I guess. No, that's me. So let's see. So we'll just wait. maybe GPT OSS 120B might be too hard on this computer. I can see that it's working. It's trying to generate, and the GPU is working too. This one is probably working for recording. Yeah, it's like they were pushing this mini PC pretty hard, which is cool. This is cool. This is like a long term review of the Minis Forum X AI X1 Pro. Okay, that's interesting. Now it's made some changes. So the emulator uses a dispatch table, a Python dictionary that helps map. I just added helped. That maps every opcode value to a dedicated handler method on the GB CPU class. This replaces the previous large if else chain. I don't think we need that. This is probably not necessary because it's we never implemented it, so we can just get rid of that. Okay, and then decoding dispatch, opcode handlers. Okay, the main execution loop becomes something like this. So opcode equals that. We'll fetch additional byte. Otherwise, we don't. We'll find the handler. If handler is none, we raise an implementation error. Otherwise, we invoke the handler. Great. So CPU class, not really. We'll edit this later. But handler design, each opcode has its own method. NoOp LDBC-D16 that implements the exact semantics, updates registers memory via encapsulated state, and returns the number of cycles consumed. Okay, sure, but not exactly though. But we'll handle that later. Documentation testing. Every handler includes short docstring with mnemonic affected registers, flags. Okay, and cycle count. Unit tests. Sure, that's ideal. And this approach makes opcode documentation readable, extensible, and easy to test for future contributions. Okay, sure. Let's just keep that for now, and then we'll refine later. Okay. Okay, so overall, I think it did well, but since I've had experience with GPT OSS 120B before, and it tends to be very overly detailed and enthusiastic to fill things in. So I think it's just a habit of the model itself. So I'll just leave it be, and then we can add more as necessary. I have no clue why I have so many of these files here. It's weird. And also I should probably set my editor to wrap some tabs. Let's see. Oops. What did I just do? Let's see. Autosave. No autosave. Preferences, wrap tabs. Okay, great. Starting to also think that maybe my font size might be too big, simply because I'm running out of space here. Okay, hopefully everyone can see this. Maybe I'll just throw this to the side to get more space, because now we have this editor here, or this chat here, getting in our way. Okay. Pylons, no. Okay. Get rid of that. Okay, now let's have the LLM finish this. Okay. Here gbcpu.py. Here is a start to the CPU class. I have a get register helper. Can you finish only this, and only this method up? Look to design.md if you are unsure about how the registers work. Do not do more than what I ask for. Okay. So let's see if it can follow these basic instructions. Yeah. In the meantime, I'm gonna check out to see if we can do some MCP servers. Oh, maybe not yet. No MCP servers. Let's configure. Oh, okay, never mind. Too much work. advanced MCP settings. Yeah, whatever. Just gonna go back here. Done. Whatever. We'll do that one day. For now, we'll just stick to traditional chat-based coding agents. You know, I have a feeling that maybe we should kind of go back to Qwen 30B. Definitely was faster. This model is probably way too big for this computer to handle. Yeah, it just takes too long to get an answer. So maybe I'll switch back to Qwen 3 30B or Qwen 3 Coder 30B and try to finish things up here. But if the 120B here for GPT OSS does well in terms of following the instructions that I want it to do with this specific CPU cost change, I have more trust in it. But this going at this pace is really not going to fly. Already I'm just like kind of stalling. So yeah, this is its last chance. It has to be very, very good here, and if it's not that great, then I'm going to switch back to Qwen 3 Coder because it is faster and we can just always iterate if it's not getting anything correct. Okay, let's check back again. Okay, this actually looks promising. Okay, what did it do here? All right. So AF returns AF, of course. A returns basically the high bits of AF shifted 8 to make it basically take the highs and shift it down so that, and then we mask it with 0xFF so that it becomes just like all zeros with the last 8 bits being whatever the high 8 bits before shifting was. So visually it could look something like this. So how this part works is, suppose you have let's say any number like 8 bits, 1010 1100. Okay, and again, this is suppose it's like 16 bits, for example, and this happens to be AF, register AF. If we shifted AF down 8 bits, well, this basically replaces that, right? So then it becomes in this case 0 0 0 0 0 0 0 0 and then 1 0 1 0 1 1 0 0. So that gets down to, oops, that becomes this set of bits becomes the last bits here, and then the replacement of these becomes 0, and then we had to mask it with FF. So imagine F being 1 1 1 1, so that's F 1 1 1 1. That's another F. I'm gonna just erase this. Then we'll AND it to ensure that anything prior to this is going to be 0. So this will be 1 0 1 0 1 1 0 0. Okay, so ANDing with FF means that everything here is all 0, so it doesn't matter what garbage this is in front. Since it's ANDed, we really only consider the last few here. So we follow that pattern for like the rest of these, and it looks like it's gotten that right. Actually, I think that I did really well here. So that's good. Thank you. But again, I don't think it's very sustainable to do it this way, to use GPT OSS. So I am going to, how do I eject this model? I'm going to eject this model, and I'm going to load Qwen 3 Coder. This is actually going to be probably better for us. And I'm going to load that model in and hope that things go faster. In this case, I'm going to change this to back to Qwen 3 Coder. So Qwen 3 Coder 30b a3b instruct. Okay, so when we're done with this and it's done loading, what I want to do is create a setter now. So wait, okay, so let's create a setter. In this case, get or set register. Okay, set def set register self code value, and it'll be as simple as if code equals af self.registers.af equals value, and then we'll just finish the rest here. Okay, let's bring this down so that it can read top to bottom. Okay, let's make one more space there, and that looks okay. Let's have it finish all of this. Check out. Okay, it's done loading. Okay, so given GB CPU, finish the rest of this setter method. Okay, so again, first time we've reloaded the server once already, so that clears out our cache. So this first request is going to take a while, but I expect that once it starts to cogen, it should be much faster than the 120B model in this case. I think we can even already tell in LLM Studio. Last time it was like every 2 seconds. It was another like 3% or so on. In this case, that looks like it really is, right? 6, 8, 10, another 3%. So in this case, we have about a minute left, minute 20 left. I can't do math. 30 seconds times 2. Yeah. About a minute left. So we'll leave it to do that. And then after it's done processing, like processing all the client prompts and our context and all that stuff, we'll see some code generation happening. I hope Qwen 3 is also just as good at following these types of instructions. Okay, now it's going. So it is much faster than GPT OSS 120B, that's for sure. But will it actually generate good code? Let's see. So this one has to set it at the top level, right? And it looks like it is. So self registers AF. The high byte is value 0xFF. Is that correct? F is the lower one, so what does that look like? Okay. Is that correct? Let's see. Okay, so F is... Okay, well there's... Oh, I forgot there was no F. Did we assume that there was an F? Ooh, interesting. Oh, well, these are considered flags, I guess. The lower ones are flags. Yeah. Okay. Well, let's talk to this thing. Let's have it check it over. I completely missed this point that there may not be an F, but let's ask. I just noticed something in in our documentation design.md, we listed out the registers, and we have high and low registers. First, check your work in get registers and set registers. are they consistent with these rules? Second, is there really an F register? Okay, so now this one is interesting because actually it ended up correcting itself. That's interesting. Okay, so let's take BC for example. B is the higher byte of BC. So we want to take whatever value, we want to mask it by FF, so the last byte. Then we want to shift it up by 8, and we want to OR it with whatever we have currently with registers BC, with only merging it with the lower bytes, because now the higher bytes here are going to be these new values. So yeah, that's okay. This looks right, actually, this logic. And I'm assuming it's consistent with the rest of these. Looking at the design documentation compared with our current implementation. Okay, the document shows that the flags register is part of AF, not a separate F register. Our implementation treats F as a standalone register, which is incorrect according to the spec. What needs to be fixed? Remove handling for F in both getRegister and setRegister methods, since it's not a separate register but part of AF. That's correct. Update documentation comments to clarify that that F is the lower 8 bits of AF, which is flags. Ensure consistency with how registers are defined in spec table. Let me fix this properly. Okay, is it gonna do it? Let's see. Okay, you can fix it then. Because we are in ACT. I thought it was going to fix it. Okay, I guess it is going. Now, just to make sure, we can also have it write some tests. So we can create a test here, test folder. Actually, let's just have it do it. Let's have it create a test folder, and then test for getting and setting registers for the CPU once it's done with this. So again, let's see how our CPU is doing. Still working really hard. Our GPU has 30 out of 31.5 gigabytes used in VRAM. So we really are maxing out. Memory, even though we've upgraded, we're still up to our next pretty much in memory. So, okay, so here it should remove this F part, which it did. Okay, so that's good. It's probably going to go through for the rest of these. Okay, next, I think we should start typing what it needs to do with the GB CPU class. So given our GB CPU class so far, with getting and setting registers, can you write a simple unit test for it in a separate tests folder and files, and in an update in documentation how to run unit tests in general? Let's keep running unit tests simple. Unit tests simple. Okay. Okay, cool. I missed that it didn't do this, so it's still working. I'm glad that it still needs to do what it needs to do without having someone incompetent like me telling it what to do. Okay, so again, we'll let it do its thing, and then we'll come back and give some attention. So far, it is slow doing local coding like this, but it is fun because it forces us to think about things and really commit to getting help when we need to. Now it's done fixing itself. Let's hit save, and then update. Well, it knows to update the documentation and create the unit test now. That's weird. Still Oh, weird. Okay. I still see the F, but let's see what it does. You know what's funny? I don't know why my GPU fan isn't spinning. I'm like kind of doubtful that either the 5090's GPU is so good that it runs so cool like this, or like more of the layers are being like offloaded to CPU, and this 30 gigabyte thing is just like a facade or like some sort of trick, because I literally the GPU doesn't seem to be working. Like it's there, but I don't see fan spinning, and I don't know if there's even any activity. Let's see. So we have what, MV top? Is it even working? It is working. I guess it's not working hard enough to get hot, because the fan is at 0% right now. That's quite concerning, but it's only using 88 watts out of the 600 watts possible. So I think the CPU itself is bottlenecking. Let's actually take a look at hardware info 64 Windows. Realize that we never really did like formal analysis of this computer. So we'll just set this one up while everything is still generating, and we'll see how our hardware is actually doing. Okay. This could be slow. Who knows? It's examining our hardware. Okay. Okay, where are we looking at here? Is there sensors? It's this sensor thing. Okay, cool. This is what every YouTuber sees, I guess. Okay, in this case, sensors. Oops. Don't know how to use this program. I'll hit save and then have it do its thing. Was it hardware info 64? HW is okay. HW64 will start. Then we'll do not check for updates. I don't care. Let's look at sensors. Let's just close this. Okay, so what are we looking at? In this case, cooling doesn't seem to be that much of an issue. CPU, as hard as it is working, it is really only up in the high 60s in this case. Package power is at 47 watts. We're not really using any NPU. I think this is actually pretty decently high, given that the CPU is meant for like 28 watt. Memory bandwidth in this case, we're going at about 41 gigabytes per second. I would have assumed that this would have been more because it's dual channel. Yeah. Do we have GPU? So this one is our integrated one. This one is the one we want to see here. Apparently our fan isn't really working. Oh, it is working now. I see the fans going. Okay, cool. It's gotten hot enough, I guess. Still, I guess GPU overall is 52C. Yeah. Okay. Sure. Yeah, so now it's writing some unit tests. Still feel something is still not quite right here. It's okay, we'll figure it out. I'll just let this thing run and have it complete, and we'll come back to it again. Okay, it's done generating a bunch of unit tests. Let's see what happens. Let's save, and then we can run it and see what happens. In this case, if let's just take one of those getting the C low byte. So 3456, we should be getting 0x56. Okay, let's do its thing in terms of updating the documentation. GPU still doing fine. Oculink. I actually wonder whether or not Oculink is holding it back. No, I don't think so. I mean, it's transferring. Maybe? I don't think so. It's mostly idle. You see that? It's like 31%. So it's not even really saturated. We gotta make this thing faster. Gotta figure it out. But what's our token usage so far? Okay, 35 out of 60. 65. Okay. Save. What is this command? Documentation. Testing. Okay. Okay, so running unit tests. To run unit tests, execute the following command from the project root directory. Python m unit test discover tests. Great. Okay. It tests right there. So we can just copy this. And then we can bring up a terminal window. And if we paste this and run, we should have tests running. So, oh, we didn't source our virtual environment. Did we even create one? We didn't even create one. How embarrassing. Okay. Create environment. We'll use VNV, Python 3. Okay, we can skip package installation. Okay, let's just bring this up again. Cool. It didn't even activate for us automatically. I expected it to. Do we not have an activate? Oh no, it's doing that thing again. This happens from time to time. I don't know why. Source.env, then activate. Yeah, so we don't have this. Okay, so I can just do Python 3 mvenv.venv. Oh, it's because we don't have it. Okay, so sudo apt install python 3.12 venv. So that's why it didn't do it correctly. So we'll just install that and we'll try again. We lacked the system dependencies, so I will remove the current venv, and let's create it from here again just to see we're not going insane. We'll skip package installation, and then let's trash that terminal, and then it should bring it up now. Yes, there we go. It's activated. Okay. What did we need again? What did we need? Oh, no test ran. Okay, no test ran. All right, let's just vibe code that. I don't know why. I don't really write Python tests. So let's add decline. And just enter. See what happens. It should have discovered this right here. Apparently that's what discover test does. So what's it doing? Okay, so execute the find command. So it did find something, but why did no test run? Let's see. In the meantime, I am quite curious actually how the 20B model would do for GPT-OSS, but yeah, let's wait. I suspect that it won't it won't do that great accuracy wise. It's a mixture of experts for like 3 billion active. I heard that it isn't that great either in comparison to whatever else is out there. Oh, it apparently can't Okay. Yeah, it can't create empty files apparently. Or it can. Let's see. Is it smart enough to retry because of the init.py? This has to have been tested once before. I'm also going to experiment with adding, well, at least swapping this 5090 with another card that I have that I use, and see how it performs at a lower spec. Already it's pretty bad with just a 5090, so I wonder if we can just save this and move on. How about this? Oh, okay. There we go. It touched instead. Okay, that's cool. So I don't like how it like loses focus or steals focus on everything I do. Whenever I'm like on a text box or something and it does something, and then I just end up jumping to the next place. Okay, so it ran 26 tests. That's cool. It works. Great. Let's see. Nice. So unit tests are good. Let me mess around with this and see if it actually is really testing something. So this should actually have been 0x12, but I'm going to just change it to expect 0x13 and see if it's lying to us. Ah, yes, we have one failure. That's good. Okay, that's good. Okay, so we have tests. Yay. Okay, cool. At this point, I think we should really start checking things in, right? Like we should get add, get status, get commit, GameboyAI, get push. Okay, I've switched to, well, at least I'm going to switch to GPT OSS 20B with Klein. But I think the next thing we need to do is document the memory map so that we can implement the memory map. And so I'm going to try this one more time. I'm going to take a screenshot of this memory map here and have a small model like Qwen 3BL4B. Turn that into Markdown and copy and paste it into the documentation, and we'll see what happens. So making it very easy, we will just take a portion of what we really need, and then we will just give it some detail. Okay, this is the memory map of the Nintendo Game Boy. Can you turn, or let's not be so indecisive. Turn this into a markdown table. Okay, let's see what it's gonna do. It's really fast because this all fits into GPU memory, and I think it does it pretty easily. Yeah. So GPU is finally saturated. Here you can see that we're at now, I guess, close to 90%. GPU is a little warmer now. We're using a little bit more power, so that's good. Yeah, finally, and I finally feel the heat on the heatsink. I like how the Oculink helps me understand how hard the GPU is working by just like touching it all the time. I think one of these days I'm gonna do something bad to it though if I keep doing that. But yeah. Okay, so here is the table. Let's just double check. How do I do this? Let's just tuck this in, and then we'll tuck this one here. And then, okay, so yeah, 00003 FFF, 4000, 7 FFF, 8000, 9 FF. Right here, 9 FFF is wrong. Okay. The rest, I hope, is fine. FDFF, so we'll correct that. Okay, you know what, let's just copy that and then we'll just correct it. It is better than copy and paste. It's a cleaner copy and paste in this case. Let's just tuck that aside, and then oops, I keep doing Control Shift V, but it's just Control V. Okay, So the first thing we need to correct here is going to be this one here. This is actually 9FFF. The next thing is going from E000 to FDFF, FE00 to FE9F, okay, FEA0 to FEF0, right? So FEF0, FEA0 to FEFF. Okay, let's correct that. FF00, FF00 to FFFE. And then FF, it's missing FF. Is it missing? It's missing FF80 to FFFE. Wait, oh, missed that one. Okay, and then FFFE. There we go. Okay, IO registers. Is that it's starting to? Okay, it's missed something here. Let's just first. Does this even look right in Markdown? Let's just see. Okay, it is valid though. Okay. All right. So from cartridge, usually a fixed bank. Okay. Switchable. Okay. Video RAM. External RAM. Work RAM. Work RAM. Okay. Echo RAM. Mirror of C0000DDFF. Nintendo says to use, okay. Object attribute memory. Not usable. Okay. And then FF00. We're missing this one right here. So it skipped that one. So let's edit it. So let's just take maybe this line here. Go down. What was it? FF00 to FF7F. And then this one is IO registers, and this one's actually high RAM. So it's not perfect. It's only 4 billion parameters. So, and it's also quantized. High RAM, HRAM. It looks like it tried to do it to here. So I have no idea what it is doing. Oh, okay. So high RAM was... Okay, so it got confused here. So I can just probably get rid of that. And then interrupt enable register IE. Okay. So what does that look like now? This IO register should have been... Uh-oh. Wait. I think I need to refresh this. Preview. Okay. High RAM, that's still wrong. Oh, because I copied and pasted. So let's see. Again, this should be the proper table. Okay. That is the proper table. All right, so this is the right memory map. Now, let's try telling GPT-OSS20B to clean this table up because all this white space is driving me nuts. So let's go to LM Studio. Let's eject. Let's start the server again with Unsloth's version. We'll load the model. Should go pretty fast. And then let's pop up client again. And then select all this. Let me do that. And then we'll say in design.md, look at the memory map. Let's just do this. Memory map section. And clean up the markdown here. There are a lot of white spaces in which I feel is unnecessary. One thing at a time for this person. And we are loaded. I have increased context. Let's go. So let's see. Okay, again, it's gonna take a while because I had cleared cache, but it is faster because it's a smaller model. It's going all on GPU, and it should go any moment now. Okay, cool. Now it should be very fast. And let's see how fast it is and how accurate. So it's going. It's doing some of that cleanup. It looks okay, I guess. Okay. And then let's double check. Okay, so let's double check from the original. See if it didn't like rewrite anything. So 0003 FFF, 4000 7 FFF, 8000 9 FFF, A000 BFFF, C000 CFFF, D000 DFFF, E00 FDFF, FE00 FE9F, FEA0 FEFF, FF00 FF7F, FF80 FF FE, FFFF, FFF. Okay, so it is good. It is good so far. Okay. Now that we have that, let's also say, well, let's see here. Okay. Let's not worry about that one right now. Let's just worry about this one. Okay. In memory, we can say gb memory.py. Let's ask it, can it implement a simple memory class here? So we can start it off with class memory, and then def init self, and then we can say self dot memory is I don't know, a list. Okay, and then we say set a value, add self address value, pass, and we can say, well, def get value is going to be self address, pass. Okay, so we have how much context left? 131K. Let's do it. Okay, so look at design again, design.md, the memory map section. Can you implement minimally the gbmemory.py class to follow this memory rule, mapping rule? Okay, I am trying to create a Game Boy emulator. The memory class will probably be accessed from GB CPU. At least use it as a base for coding style if you don't think it really belongs in that GB CPU.py class. Or think an instance really belongs. An instance of memory really belongs in that GB CPU.py class. Okay. Let's see how fast it goes to implement something. And then we'll have it write unit tests again. So that's cool. Look at it just go. All right. Okay. So I don't like this Unicode, so use only ASCII here. Oh. Okay. So memory none. So this is dependency injection. Okay. So that's dependency injection in action here. I like how it's like literally importing it. I guess that's right. I mean, either you use a default or you don't, kind of thing. Injected probably for unit tests. So that's okay. That's an okay pattern to do. Okay, so let's see what it did right here. First, I really don't like how it uses Unicode, so let's tell it to, okay, in gbmemory.py, can we not have Unicode inside these string comments? Okay, let's see if it actually ends up fixing the entire file. So it's fixing it with ASCII, and I think, okay, now do it for the rest of the files. Okay, let's see if it notices. Actually, I noticed that. Okay, can you do it for the rest of the file? Cool ish. What's it doing? Why is it loading ROM? Wait, I didn't ask for it to. Wait, reject. I meant to remove Unicode. To remove Unicode from the docs, from the comments. Okay, there we go. How many instances? 8-bit, okay. That was it? No, we have one more here. Let's see. I still see some here. Cool. That's good. Okay. So all this does is map address is it just, I guess, checks to see if address is falling in between the address. Oh, this one too. Let's see this one too. To see if it's in the range of the 16-bit address space, and then here C000 to DDFF. If we look at the memory map here, wait, DDFF. Hey, how did it come up with this? E0. Oh wait, sorry. E000 and FDFF are both work RAM, echo RAM, mirror. Okay, so is that true? Well, yes, it is. Mirror of C000 to DDFF. Use of this area is prohibited. Let's see. Set value. Okay. Well, I guess it doesn't matter because it's an echo. So map address. It's just gonna map back to this range instead by subtracting this value here. So that looks okay. Get value. So we had to always map address to get the index first. Okay, cool. Now write tests for gbmemory.py under @tests. I wonder if it's gonna follow the same style. It looks like it. Okay, save. So if we were to execute the tests with the same thing we did before, discover tests, well, I think we need init.py too. So we'll fix that. We don't need AI to do that. Okay, cool, 30 tests. We ran 30 tests because there were only several. Okay, I'd like tests to be more comprehensive, please. Okay, one more. Okay. Let's see. 1, 2, 3. That's enough. Okay. So now we should have still 30 tests. Oh, I just saved it. Okay. Cool, 32 tests. That's fine. Okay, so we have echo RAM mapping, initial size, boundary addresses, multiple writes and reads, address out range. That's okay. Yeah, that's okay. So we have basics. Bad commit message, but yeah. Okay, now I really think it's good for today. I think this is a good one. This GPT OSS 20B is good enough to get some basic work done, and then with a combination of a VL model, we could do a lot of table extraction to update our design document and give context back to the LLM so that it can do things correctly. So let's try and see how far we can go with this.